Welcome everybody to the second most interesting session of the workshop. I know you each have your own favorite session, but this should be the second most interesting. However, we have a missing, very interesting talk by Joyce Penn now. She has some emergency to deal with, so she cannot attend. So each of the speakers will have 5 more minutes for the discussion or the talk. Okay. The first most interesting thing about this session is that there are 3 kings and 1 servant. That's me. The first king is Pao-Kuan Wang, give a presentation on the deep convection cross-tropopause transport of water vapor, which should be very important to global climate. And let's welcome Professor Wang.
Thank you. Okay, thank you, JP. As the title says, I would like to talk about the deep convective cross-tropopause transport of water vapor and its impact on global climate. So, first question is, why do we care? Well, we all know that water vapor is the most important greenhouse gas in the Earth's atmosphere and is responsible for the majority of the warming of the Earth system. As far as I know, there's still debates, what do you mean majority? Somebody says 80%, somebody says 90%, and there are a lot of different opinions. But all agrees that its total impact is greater than that of the carbon dioxide. Water vapor and infrared interaction in the stratosphere is 2 to 3 times orders of magnitude greater than that in the troposphere, and certainly that should be important, if not the most important, to consider when you talk about the climate. But the water vapor residence time in the stratosphere is most likely longer than a year. And it really depends on how high in the stratosphere we are talking about. And so in that case, it can become an important climate forcing, because if the concentration of water vapor changes in the stratosphere. And so the question then is whether or not the stratospheric water vapor concentration changes. And the answer is yes, because according to some observations, you can see that over decades it goes up and down, and in the course of about 30 years, the change of concentration of the water vapor in the lower stratosphere can be as much as 50%. And 50% change of concentration there should be of some importance. Okay, so the next question then will be, how does water vapor get into the stratosphere? And there are several possibilities, and at least 3 which are considered most relevant. The first one is the largest scale ascent proposed by people in the late 1990s and early 2000s. But it's a little strange, because as we know, larger scale usually is subsidence instead of rising motion. And so to say that the larger scale motion is responsible for the vertical transport of water vapor into the stratosphere is kind of hard to understand and difficult to measure for sure. And so far there isn't really any credible measurements. The second is the oxidation of methane from the higher stratosphere, and as you know, the oxidation produces carbon dioxide and water vapor. Somehow this water vapor would have to descend into the lower stratosphere. And that, first of all, the process is unclear. Not many facts are known there, and there are some recent estimates saying that that component should be very small. So at least in the lower stratosphere, that part is not important. And so the third one, which is the rapid convective transport, that is basically produced by the thunderstorms. So globally, you have many thunderstorms going on every day at any time, and they can transport water vapor into the stratosphere. And currently, I think this one is the major container mechanism for transporting water vapor into the lower stratosphere, at least. This now seems to be accepted more and more, but at one time it was not accepted. And I remember in the year 2000 when I gave a talk in the MS annual meetings, there are about 300-400 people down there, and almost everybody shook their heads. They didn't believe it. But now the evidence is mounting that, and there are a lot of evidence saying that should be true. Most of our evidence came from the satellite observations, and this one is one of the first. Here is a thunderstorm system occurring in Balearic Islands in Spain, and you can see at least two big thunderstorm systems. A very severe one, and you can see that this is the regular amble if you look at the satellite images, and you find out that above the ambles, there are another chimney smoke-like features on top of the amble. For a storm of this severity, the ambles usually is already located at the tropopause level, but these plumes is even higher than the amble and produce a shadow. According to some estimate, this one is about 3 to 4 kilometers higher than the amble, which means that this plume is actually 3-4 kilometers above tropopause. Well, that is in the stratosphere. So the question is, where do you get this water vapor? We know that the stratosphere usually is very dry, 3 to 4 ppm of water vapor, but in order to form this plume, you need to have a lot of water. Turns out that this is actually coming from the storm itself. And here's another example. That plume can be very wide, very large, as in this case. You can see that it goes all the way, even longer than the storm itself. And the scale is a few hundred kilometers. Certainly is not a small amount. And whether this phenomenon occurs only very, very rarely, as some comments before, it's maybe 10 years ago, people asked me, well, okay, maybe what you said occurs, but it rarely occurs. Only you have supercell or something that it produces that. But no, actually it occurs all the time. And as you can see in this image here, this is a ghost image, and you can see that almost all active thunderstorm cell has a plume on top of that. So it appears that at any time when you have a thunderstorm that is powerful enough to reach the tropopause, which is often occurs, it appears that these plumes phenomena occurs almost, well, if not invariably, occurs very, very often. So I think this is actually a rule rather than exception. Here is a loop of satellite images of the development of some thunderstorms in the Midwest of US. What you will see is that when the sun angle is high, it is not very easy to see, but when the sun angle is low, then you can start to see the plume occurs on top of these thunderstorms. And so you start to see the development of the storms, and eventually you will see on top of the storms, you see those plumes. And the cast shadows on top of the ambles. And so that says that this actually occurs all the time, and you can see almost all these active storms have these plumes. And it means that thunderstorms of the world actually inject a lot of water vapor into the stratosphere day and night. And the amount is that we don't know how big, and it is worthwhile to study. So in order to find out how this occurs, we look at these cloud model results. This is a cloud model we produce in our own group. And here is a central cross-section of the storm, and you focus on the top of the storm. You can see these plume injections into the stratosphere. And even from the overshooting top, you can see some kind of plume structure stretching out from it. And just quick replay again. So the locations and the height of the plume seems to be fairly clear from the model. This is a simulated cloud top view simulating the satellite images. You can see that indeed you produce plumes from both the overshooting top and also from okay. So what we see after we make many analysis is that the plume is produced by both the instability, so there's some mixing instability occurs near the overshooting top, and also the mesoscale, well, this so-called mesoscale here tends to at most maybe 100 kilometers, so it's not thousands. But you do have these gravity wave breaking on top of the thunderstorms. When this convective cell develops, it impinges on top on the tropopause. Normally, the tropopause is a stable layer, but during this thunderstorm time, if the condition is right, you can induce the wave breaking. The normal wave motions of the gravity waves, of course, is adiabatic, but when you have wave breaking occurs, it becomes non-adiabatic or diabatic. And only during this diabatic, you can see the injection of matters from one layer to the other. And so the white contour here represents the isentropic surface, the potential temperature. And you can see that the plume actually goes through this isentropic surface, which means that it actually penetrates through the tropopause into the stratosphere. And the signature of this wave breaking is very clear. So what happens is afterwards, when we look at this result, it reminded me what Ted Fujita of the University of Chicago talked about in the 1980s, what he called the jumping cirrus. At that time, he says that when flying above thunderstorms, he observed that the cirrus jump up from the thunderstorms and actually go against the winds. And that caused a lot of people to disbelieve it, because cirrus is a very thin cloud and you cannot actually move against the wind. And he really had a hard time to publish his results. Well, it turned out that he was right. His observation was completely correct. And his descriptions completely fits what we now observe as the wave breaking. And so here is one example of the photograph taken by Martin Sedbak, who is my collaborators from Czech Republic. Here is a jumping cirrus. Here is the overshooting top, and that's the amble. And this is our model result. Here is the overshooting top. This is the jumping cirrus. So you can see that the two seem to correspond very well in position, magnitude, and orientation. So what happens is that the jumping cirrus seem to really jump against the wind. It is wind is from left to right, and the cirrus is indeed jump against upwind. And really it's not much of a jump of the cirrus. Actually, it's the wave breaking is going against, as long as it's the wave breaking, this is okay. And the cirrus form in these breaking waves. Here is a loop somebody sent to me from Switzerland and showing that indeed you do see this kind of wave breaking. And so if you observe, look at the cloud top here, you see this wave breaking. So everything you see here corresponds very well. And we actually have to make a specific simulation of this particular case, and they look exactly the same. You have the wind shears from left to right, but you can see the break is basically go against wind. Of course, when the thunderstorm is moving closer, it is harder to observe. But they are, so recently I have found even more examples. So this is the overshooting thunderstorms on top of another thunderstorm here. And you can look at the top here. A lot of these injections of just like breaking of water waves over the ocean surface. And this is certainly a diabatic process. And many of these actions that's going on. Okay. So now how do we know it is really above the tropopause? Well, we are lucky to now have the so-called CloudSat. CloudSat data, this one is a MODIS, the regular one, and we see that they happen to correspond to each other. This is the MODIS image, and you can see that there's a track of a CloudSat represented by the red line, and we focus on these two. The red point to a overshooting top, and the black is pointing to a plume feature. And the next image is the corresponding CloudSat image. The CloudSat happened to go through this thunderstorm here, showing that the overshooting top here, and then there is a wave breaking occurring right in the downwind side of this thunderstorm. And the tropopause is right here. This is in the southern hemisphere, so that you can see that the wind is just opposite. But anyway, this pretty much proved that yes, indeed it happens. And finally, Martin just recently, he's a fanatic of this thing, so in the airline, you can see that you have a jumping cirrus, and then it actually gets blown by the wind and just becomes a plume caught in action. So there are a lot of this evidence showing all this case. So this is related to the global water cycle. In 1995, Houghton et al. Showed that you should have had water going up through here, go cycle through, and making a loop in this sense. So the major water source in the stratosphere should be from the tropics. Question is that in 1998, Highwood and Hoskins said that the tropical hot towers mostly top at 14 kilometers. So how do you get up to the tropopause, which is 17 kilometers? We believe that it is possible, and you can still produce a wave breaking on top of the thunderstorms in tropics. And here is one simulation we did to remove all the wind shear to simulate tropical thunderstorms, and you can see that you can form a kind of pancake cloud on top, and that is indeed the case here. And does that occur? Well, it turned out to yes, indeed, you do observe that kind of pancake cloud. This is a picture taken by Po-Xiong Lin from NTU. So that indeed occurs. So what's the importance? Well, in year 2010, I think, this is a publication by Susan Solomon et al. They say that these few years, the IPCC models actually overpredicts the warming. And the reason they thought is that they did not take into account the decrease of water vapor in the stratosphere from about year 2000 on to about now. So in about decades or so, there's actually a cooling occurring, and that caused the model to overpredict. If you consider the thinning of the water vapors, then you can actually decrease as represented by these red lines. Of course, this is a model, and you can tune this anyway, but at least that says that the water vapor will have some impact in the stratosphere. Well, just a few days ago, as you remember, well, you may not have noticed that the Economist says that the temperature has been flat for the past more than a decade, and there's a hiatus what happens? And you can see that this is, you probably know more than I do on these results. And there are a lot of things to be said, and what causes this. And certainly it says that something for people here really to think. You really have to, as climate modelers, you have to think how. And I think one of the things is that we probably don't understand the climate forcing of the stratospheric water vapor on the climate yet. And I rely on our smart climate scientists here in this room to resolve these kind of problem in the next few years to come. Thank you.
Questions? Anyone? Yes.
I think one of the mechanistic model that I observed of the water vapor transport cells here that you probably didn't mention is in this picture where you see the countdown of the process does not really penetrate the pole. However, the cow ice with a consistently ascending motion, it will reach the cow ice. The fast scale velocity is larger than the sedimentation force ice, so it came to the surface and evaporate. I believe that actually probably the major source.
Even in the tropics?
Yeah.
Yeah,
okay. Model this is the major source. In observation, we don't know if there's any observation to back that up, but that's what I observed, and I believe it's probably much, much larger than any source.
I totally agree with you. We are working on the possible observations by satellite. There seems to be some evidence now because there are sporadic aircraft observations showing that indeed it occurs. But the question is, in larger scale, how important that is? What is the amount? And so I would like to see that, and I would like to see how this can be implemented in the models.
Other questions? Jane?
As well, there is always, the large scale dynamics will always tell you, it's probably one of the 20 or something, the convective effect actually reached the tropopause even. So the question is really whether that's, the water supply will be persistent. And there's a lot of other products. I usually do the physics, chemistry part of this business. So there's always thought about the surviving time once you shoot into a lower stratosphere, whether these, you really change the lifetime of water vapor and other chemical species, because there's maybe the dynamic compensation. Wave breaking is one of them. It's not just one-way transport. So just thought about, what's your take on these large-scale arguments? It's not always persistent.
Yeah, well, I think there are questions about it, and we have to take it seriously. But that is also an opportunity for us to really do some study, do observations, especially to say how important that really is. Certainly, this is one of the important sources, and I think we have seen also the evidence from some chemistry measurements. For example, the ratio of heavy water to regular water measurements, because as Litzmoyer and Wang Yiling, the group has shown that the ratio is much higher than anticipated from the so-called larger scale ascent. And at least the current only possible explanation is by these rapid transport, either in the form of ice crystals or in form of water vapor. And so at least there is some kind of evidence there that we can rely on. So the question now is quantitatively how important that is. And of course, I feel it is important, but let's try to do more observations, including a lot of chemistry observations, so that they corroborate each other to say that quantitatively how important that is.
Okay, Professor Wang.
I just thought about maybe you can use some of the isotope measurements to track where the water vapor comes from.
Yeah, that's what they did. This the heavy water, the HDO.
Yeah.
That's the HDO is hydrogen deuterium water, so it's not H2O, but it's one of the hydrogen was replaced by deuterium atoms, and that's exactly what they show is, according to simple large scale ascent, it should be very small, but the actual measurement shows it's actually many times larger. Yeah, 3 to 4 times larger. So it's puzzling how that occurs. And currently, the only explanation for that is by this very quick transport, because heavy water is easier to condense. So they should decrease as the air parcel goes up. But if the transport is so rapid, they don't even have time to condense. They just go all the way through. Or they already formed ice crystal and they don't have time to go back, but they get ejected over, just like you have seen in the movies. This ice crystal just ejected directly into the stratosphere.
One short comment. If you look at the water vapor sounding near the tropopause, you'll find it's very layered, many layers. I think it's probably related to this spume.
Yes, I believe so. And actually I have commented to some other people, but many of them saying that these high-level observations are very noisy and they don't believe it, you know. But we want to measure them directly.
Okay, we borrowed 1 minute from you. So one more question.
Well, I mean, I'm the first one. I mean, this is my first question. So it's already his second. In comparison to, because we know that with global warming, the tropopause is getting higher.
Yes.
That means near the tropopause, there's extra water vapor now. That should be, my feeling is a larger effect than this overshooting extra water.
Okay, I believe that's for the modelers to figure out to how that happens. But there is, as we know, there is a interesting correlation between the water vapor there and the sea surface temperature. So often you find out that when the sea surface temperature warm, the water vapor up there is less. And that is because it pushes the tropopause higher and it causes more freeze drying, cause more ice crystals to fall back. So at this point, I don't think we have a very good idea exactly what happens in the tropopause layer there and what will be the impact of the amount of water vapor in the lower stratosphere. I think what we're talking about here is actually the variability, not just the net amount. And the net amount of water vapor in the upper troposphere certainly is higher than the lower stratosphere, but we're talking about the amount of change, which can be up to 50%, then what will be the impact on the climate model predictions? And so in that kind of frame is what we should think about.
Okay, due to interest of time, let's thank Professor Wang again. Thank you.